Hi, I'm Mike Tully. I'm the President and CEO of Aerial Services. ASI has been doing remote sensing and mapping now for 50 years. Using manned aircraft, we provide LiDAR and imagery for many verticals, including oil and gas, transportation, agriculture, for both private and government clients. For most of the last 50 years, we've used manned aircraft and large, very expensive, high-quality sensors. But in the last 7 years or so, we've been using drones increasingly and for a variety of remote sensing and mapping projects for things like dam inspection and modeling, agriculture, transmission line, and transportation mapping. Since the FAA Part 107 rules were released in 2016, commercial UAS data collection is picking up. Although the size of the UAS market under Part 107 is just a mere fraction of what it will become once beyond visual line of sight flying becomes a reality, today there are some mapping applications well suited to drones and new applications coming along that are tailored for drones. It goes without question that drones have dramatically lowered the barriers to entry into remote sensing and mapping. That's a good thing, but it cuts both ways. Increasing numbers of new remote sensing and mapping practitioners flying drones are unfamiliar with photogrammetry and other principles of remote sensing and mapping. Some practitioners are making unfounded, erroneous assumptions or claims about the positional accuracy of their mapping products. This session is a discussion about the principles of remote sensing and mapping and how they apply to drones. Specifically, we'll answer the question, what is positional accuracy and how do I know when I have it with my UAS map products? Principle number one is that positional accuracy is the final product of detailed planning and diligent work. Accuracy does not just happen. It takes hard work and is based on principles that don't change. The nature of things does not change simply because a new guy is flying a new contraption up in the sky. Its accuracy is not purchased with the drone. It requires skill, careful, informed planning. It requires a knowledge about the concepts that we are about to go over, and accuracy is a value add that we as the practitioners provide to our clients. Principle number two, all measurements contain error. Consider a simple case. The most accurate ruler cannot measure distance without some error. This ruler is only good to 1/10 of a unit, maybe a 20th if you stretch it and interpolate between two marks. A more accurate ruler exists that can be used to quantify the error of your measurements made with this ruler. But even if we understand this ruler's inherent limit to measurement error, it may still be used ineptly to provide unmerited assurances of accuracy. For example, most of us use ArcMap. Just because ArcMap, or whatever desktop GIS you might be using, just because it displays values to the 1/10,000th does not mean that number or distance, whether it's a GSD, a ground sampling distance, or a coordinate position, is accurate to 1/10,000th of a unit. The accuracy of your data is determined by the quality of measurements, not the resolution of your software. The ruler in this case does not convey the accuracy to your data. So just like with the ruler, if I claim that my data is good to the 1/10,000th because my GIS says so, then I'm overstating the nature of my data and misusing this ruler without consideration of its inherent limitations to characterize my data. The old adage certainly applies with drones and remote sensing that says garbage in produces garbage out. The scary thing for all of us now is that while we are still in this Wild West stage of drone application to remote sensing and mapping, Many practitioners don't even know they're producing garbage and trust that because the ruler or the manufacturer says it's good to 2 centimeters, that their mapping products are inherently that accurate. That brings us to principle number 3, which says that the entire drone system, the aircraft and the sensors, the operation of the aircraft, and the software used to process data determines the total positional error of products. It's the system, the entire system that contributes to the final accuracy of products. It's important to appreciate that all those components of the drone system are making many measurements. Each observation by each component of the system is erroneous. All of this error accumulates and can become excessive if not managed skillfully. For example, aircraft performance. For good aircraft performance, it requires the pilot the UAS skillfully, requires good favorable weather, a flight management system that's used correctly, and stability within the air. The best, most accurate system, drone system, in the wrong hands will produce junk. Weather, wind, visibility, ground conditions, all of these things affect the accuracy of the drone system. The camera lens, the GPS unit, the inertial measurement unit, and other sensors also contribute to the overall accuracy of your data. For example, one problem we could talk about to illustrate some of this is the rolling shutter problem. Today, drones are commonly equipped with rolling shutter cameras. This type of camera is inexpensive and creates great videos, which is why it's so commonly used on drones. But the rolling shutter effect on imagery is prevalent and introduces a new source of error that must be modeled out properly. This serves as a significant obstacle to extracting high accuracy measurements in photogrammetric software unless that error is properly managed. Typical DSLR cameras using CCDs as opposed to CMOS sensors use a global shutter. That is, they capture an entire frame of imagery at the same instant. The shutter opens, then closes in a millisecond or so. But other cameras, generally CMOS-based cameras, that are used by many drone manufacturers, use this rolling shutter. This shutter captures the entire scene in pieces across time. This, in turn, produces distortions in fast-moving objects. In remote sensing and mapping applications, especially where we're flying at less than 400 feet away from features, pretty much everything is always moving rapidly. We may not be able to see these distortions in a typical ortho, but they are there, and they impact the quality and accuracy of all our mapping products. Pix4D and other processing software manufacturers do attempt to model out these distortions, but the rolling shutter effect is an added source of error to many camera systems. Drone systems that use global shutters do not have this source of error. Which type of camera are you using? Do you know? Many practitioners don't. So it's the entire system that contributes to the accuracy. The quality and the accuracy of the ground survey is important and contributes to that error. The accuracy of your ground control points can have a big impact on the fidelity of accuracy measurements possible. The number and position of ground control points will have an impact on positional accuracy. We'll talk about this more in a little bit. The processing software used with your drone has an effect on error. It can be used well or poorly. There's the aero triangulation, the digital surface model or digital terrain model calculations, and the orthorectification. These three processes are bundled into your processing software somewhere, and each of those processes makes measurements, is calculating things, and are contributing to the total air budget of your mapping products. The processing skills of technicians also have an effect. Like we said earlier, the best software in the wrong hands will produce junk. All of these data processing tasks require considerable understanding of the processes, the nature of your data, and what products are being produced for what purpose. Failure to grasp any of these things can negatively impact map product accuracy. Decisions about which software option to use are important and often differ depending on observations about input data or output objectives. Some software makes trade-offs between the ease of use and the ability to manage the processes and the inherent error of them. Did you know that? Which are you using? The easy-to-use software or the very flexible software? Poor file management is another part of data processing that can really mess things up and destroy the accuracy of your output product. Drone manufacturer claims of accuracy are really limited to just the drone and maybe the packaged sensors. All of the other system components on this slide affect the deliverable accuracy for your project as much or more than the inherent accuracy of the aircraft and sensors alone. These manufacturer claims really express simply a theoretical maximum accuracy on what could be achieved. So read the fine print. All of these components of the drone system introduce discrete sources of air, and the project, any project, normally has some type of accuracy specification or intended use that expresses the client's expectations of accuracy. The entire drone system's error budget needs to be quantified so you are confident these accuracy specs can be achieved and so you don't exceed your error budget, or if so, help you determine that another more accurate drone or sensor or pilot or etc. with a smaller cumulative error is needed. Unfortunately today, many of our drone systems' error budgets are unknown. We just haven't been using these systems, the components of these systems, long enough to understand how they perform in different environments and in different conditions. And the only way to quantify the cumulative errors of these systems are to systematically test the positional accuracy of their products. Product specs are important and need to be carefully reviewed to determine the right tool for the job. Is a drone even needed? If so, what type of sensor? What are the accuracy specifications? Will weather factors be a problem? Will the drone be stable enough in the expected weather? Can I use a vertical takeoff and landing system, or should it be a fixed wing drone? Can the project be accomplished under budget? All of these factors affect our choices and ultimately the air budget of our system. Principle number 4, accuracy standards do exist and are important. Our mapping often must meet some expectation of accuracy. That is, it's up to us to quantify the error in our products created by our drone systems and ensure it is less than some acceptable amount. Much of the work done in remote sensing and mapping is done to meet some accuracy standard, but many drone practitioners don't know that these standards exist, and more importantly, don't understand how to quantify the accuracy of their data. Many may be familiar with the new ASPRS standards that were updated a couple years ago for digital scaleless data. The USGS have their own standards. We still see the old national map accuracy standards used in solicitations by uninformed clients. And if you run across these, just make a note that these are old, outdated, and inappropriate for modern data. The NSDA, or the National Standard for Spatial Data Accuracy, is often confused as an accuracy standard, but it's not. It is simply a prescribed method of reporting accuracy statistics that is used by the different accuracy standards. Many clients will use accuracy specs that dictate NSSDA reporting, and that's a good thing. Principle number 5, ground testing is always recommended for mapping, but may not always be required for your project. Your new SenseFly drone says it can meet a positional accuracy of plus or minus 5 centimeters, and I'm just making this up. But because of what we just talked about, how do you know that your data from that drone system meets this level of accuracy? As discussed previously, only a portion of the accuracy achieved in your mapping is determined by the aircraft and camera. That being the case, how will you know what the positional accuracy of your mapping products is if you don't test it? Answer, you can't. The only way to test is to use checkpoints. So unless you know from repeated testing of your drone system, the operators, the aircraft, the sensors, the software, the processing procedures, etc., that it repeatably and reliably will meet a certain positional accuracy, you have to test the products. Or you could tell your client that it might meet that accuracy, but that you really don't know. Manufacturer claims have little to do with the real-world achievable accuracy of your project. You shouldn't use the manufacturer's tech sheet to quote your capabilities. I understand that it's aggravating to tell your bosses that I can only guarantee 10 centimeter accuracy after he forwards you emails from service providers claiming 2.5 centimeter accuracy all day long. Educate him about achievable, repeatable accuracy, not pie-in-the-sky accuracy. The biggest point of all is control and checkpoints. You can never have too much ground control and checkpoints, and typically you can't, as a professional, afford to eliminate ground control and checkpoints because you typically need to know objectively what the accuracy of your products is or have a good estimate of that. Principle number 6. It may seem intuitive, but you can't test the accuracy of something without a standard or a tool that is inherently more accurate than the thing being tested. The positional accuracy of ground control points or checkpoints must be surveyed to 3 times more accurate than the required accuracy of the mapping products. Your survey must be good, so make sure that you get a surveyor that understands how this is done. You need to know 2 things to control a drone mapping project correctly. How many ground control or checkpoints are needed, and where should they be positioned? Careful positioning of each point within the AOI and knowing the number of points needed is critical. If the points are surveyed to 3 times better accuracy but are not positioned well, or there are too few points, the points may not sufficiently or statistically test the accuracy of the mapping. This graphic is simplified. You will often have less rectangular shaped areas or other factors that may require more points than noted in the slide. But the important thing is that the points positioned around the perimeter of your area and 1 or 2 in the middle are very important, especially those 2 or so points in the middle of the area make a huge difference in reducing the positional error. Principle number 7. All positional accuracy methodologies have limitations, especially when the number of checkpoints is small. It's not always feasible to measure ground control points because of fragile terrain, unreachable spots, personal safety concerns, or project budget. Control does add expense to the project. While the planning and the surveying or measurement of ground control points could take hours each time, the post-processing of those points normally only takes 10 or 20 minutes, so it's not a big cost on the backside of a project. Statistical theory says one needs at least 20 checkpoints to estimate positional error in a population of data. What we're trying to do with checkpoints is measure or estimate the cumulative error introduced by our drone system. The drone system has, for example, estimated the position of every point or pixel in our data set. Sampling error is the deviation of the selected sample, our checkpoints is our sample, from the true characteristics of the entire population. This slide shows two populations. The one on the left has a small sample of its sampling error. The one on the right has a large sample or measurements of the sampling error of its population. The population on the left, the validity or the strength of our estimate of the sampling error will be less strong, less accurate, because our sample size is very small. The population on the right, because it has a larger sample of the sampling error, will have a better estimate of the true error of the population. So we do this by sampling the error. We measure how much error occurs in our points and pixel positions using ground control and checkpoints. But our sampling is flawed, as we've talked about. It represents only an estimate of the true amount of error because we're not measuring the error of every point and pixel. In fact, we can't do that because it's cost prohibitive. So we sample the error with our 20 or so checkpoints. To do this and have a valid statistical estimate of the error in our population, we must have at least 20 points. We often use fewer, but when we do, we cannot make statistical claims about error. We can make inferences, but no valid statistical statements about those claims. Fortunately, technology exists to help us measure better and reduce, but not eliminate, the need for ground control and checkpoints. RTK GPS integrated with our drones is one such tool that can help reduce overall ground control point costs and increase the accuracy of our products. However, things do not always work perfectly, which is where post-processing kinematic surveying is helpful. Connections to GPS satellites with the GPS unit in our drone are often interrupted or even lost in urban canyons or by excessive turns of the drone, for example. Often people who work on site may encounter these interrupted connections, which interfere with real-time corrections that are needed for estimating camera positions on our drones. The system then, when that GPS connection is interrupted, the system then gives float solutions or even reverts back to standalone or non-RTK mode. The camera positions are RTK float, indicating a big uncertainty of the corrections. The accuracy will again be tens of centimeters for RTK float, or even up to meters of accuracy as you would get from non-RTK flights. In this case, you could perform the computation afterward, referring to the ground reference recorded during flight by the base station using post-processed kinematic. One really great advantage of PPK is that it can calculate positions forward or backward in time from data recorded in the field. RTK solutions cannot use data that has not yet been recorded. So when there is a loss of lock or no GPS fixes on images, PPK can be used to back calculate accurate positions from all the other positions it obtained before and after that event. This is an added advantage over RTK alone. Using a drone with RTK-enabled GPS sensors and supplementing with PPK can reduce the number of ground control points needed to achieve accuracy specs. With this type of system, you could, for example, reduce the number of ground control points from 20 or more to 5 or so and be confident that accuracy specs were met, assuming the acquisition and processing went well and the sensors were operating correctly. Long term, getting an RTK PPK drone is often a better investment because of the savings and required ground control for each project. There is no guarantee that PPK results will be better than using 20 or more checkpoints, but it will be as good or better than RTK alone and far better than no ground control. You should always have some checkpoints on a project if for no other reason than to test that expected accuracies were met. The takeaway for procurers of geospatial data from this presentation is that anyone operating a UAS for mapping needs to be familiar with these foundational remote sensing and mapping principles and understand how to quantify errors that always accumulate in your mapping. If your UAS provider is unaware of these concepts like accuracy standards, NSSDA, ground control, error budget, then I'd look elsewhere for a service provider. The takeaway for producers of geospatial data is to understand these remote sensing and mapping principles, learn how to test or produce to meet the positional accuracy of your mapping products so you can reliably produce quality products. Be sure to check out our website and download our free ebooks about drones and a number of other articles about accuracy and remote sensing and mapping. Thank you very much.